Okay, MCT4C, we're on day 6. This is lesson 1.4b, and the 3-minute review goal is to use SOHCAHTOA to solve real-life problems. This is review of old stuff, but this is what we're working on today, and we'll see the problems will go from pretty routine that you should remember from grade 10 and 11 to some that are a little more challenging. So let's get at it. Ferd's deck will be 20 inches off the ground. Steps must have a maximum pitch of 40 degrees. How far out do the stairs have to begin to meet safety code? And just like any good trig problem, how we get started is a diagram, right? So let's see if we can draw a diagram. There's Ferd's deck here. It's going to be, there's his deck right there. And that's 20 inches off the ground. Okay, 20 inches. And must have a maximum pitch of 40 degrees. So, you know, the steps are going to be out here somewhere, but let's just make it look like a triangle. So, and the pitch is 40. So this is 40 degrees here. And the steps will be along here somewhere, but we don't have to worry about that. And I think what we want to find is how far out do they have to begin, so to meet safety code. And in this triangle then, as long as it's the deck square to the ground, we can use SOHCAHTOA. And we've got the opposite side and the adjacent side, so that's going to be the tangent. We've got the tan of 40 is equal to 20 over x. Opposite over adjacent. Now how do we solve this? Cross multiply. This is a bit strange here because we still got this number. We could put this into our calculator and get a number, but let's do that all in one step. How do I get rid of that and have x alone while I divide it on both sides? And that number, when you jam that into a calculator, 20 divided by tan 40 is around 23.8, and the units here are inches. You know, and this is a little strange. When we finish this off, we're gonna be satisfied with this, but the steps will be out 23.8 inches, and this isn't, you know, if you said a dimension to Mr. Faber in construction class, 23.8 inches, he'd probably glue your head to the table because you're mixing up decimals in inches. This would be about 3/4 of an inch, right? 0.75, and that's the way it should be if you're talking in inches. But you know, we don't really care about that. Just don't say it to Mr. Faber. And that's the end of the 3-minute review, and we'll see the problems in the lesson are fairly similar to this. So let's just keep going. Here we are, solving problems in right triangles. And there's actually two pieces of this. We've pulled questions from 1.1 as well, which was when we started solving problems using exact angles. So that'll pop up now and again. When we're solving these problems, there's some terms that come up: angle of elevation or inclination and the angle of depression. And some students have some trouble figuring this out. The angle of elevation is when you're looking up at something. This here is the angle of elevation. Some person looking up at a lighthouse, there's the angle of elevation. Now if you're in a helicopter or someplace far above the ground, you're looking down at something, down, your head goes down, it's like you're depressed. That's the angle of depression. Okay? And the key here is we always measure the angle of elevation or depression from the horizontal. So whenever we're in a question, we always think, you know, where's the person in the question? And you think of a horizontal coming out from them, and then they're looking up for elevation, or in the case of the helicopter, they're in here, and there's the horizontal, out like the horizon, the horizontal, and looking down. And that angle swept out is the angle of depression, or in this case, the angle of elevation. So let's remember that as we go on. Now, one thing we might be sort of wondering is, how are these angles measured in these problems? It seems a bit silly, but actually there's devices that help us, and at some point this year you're probably going to get a chance to solve some of these problems practically, or if you did maybe in previous grades. Something called a clinometer. So the idea is you want to find out this angle, the angle of elevation of this kid. He uses this little device, and he can measure how much the little straw is tilted. And this is called a clinometer. Not that important. It's not going to come up on a test, but there you go, clinometer. And there's fancy versions of these too. This one's maybe one that the science department might have, and this one would be one that maybe surveyors use. And you've seen really fancy ones on the road surveyors, but we can use these to solve practical problems. All right, so here we go. From the top of the CN tower, the angle of depression of Rogers Center is 73 degrees. Find the horizontal distance between the two. Now, there's some stuff going on here, and we see that there's going to be an angle of elevation or depression or whatever. Depression, obviously, there's the word. Let's draw a diagram. That's the important thing. It doesn't have to be too fancy here, but let's draw our CN tower. That's a great CN tower. And then over here somewhere is going to be the Rogers Center. See, there's the Rogers Center. And where's the angle, the 73-degree angle? Well, if we're at the top of the Rogers Center, we look out from a horizontal, right? There's a horizontal, and the angle swept out from there to whatever we're looking at is the angle of depression. That angle is the angle of depression. That's the 73 degrees. Right? So, okay. What do we want to find? Find the horizontal distance between the two. Well, there's the horizontal distance between the two. Question is how are we going to solve this? Well, we assume that the CN tower is poking straight out of the ground at a 90-degree angle. Well, there's a couple different ways. One would be remembering your grade 9 geometry rule. There's a Z pattern right there, so this could be 73 degrees. Another way to think of it is these two angles got to add up to 90 degrees, don't they? That's got to be 17. And so in this triangle now we've got enough information, as long as we remember to put the height of the CN tower on there, to find our unknown x. It doesn't matter which we use, but I'm going to use the 17 just for fun. From the 17-degree angle we have the opposite and the adjacent, so that's the tangent of 17 is x over 213. Now it's easy, right? Just multiply by the 213 and jam that into a calculator, and we get about 65 meters. These word problems, we got to write a sentence, and this is always fun for me to have to write this. The two are about 65 meters away or apart. You can write sentences just as good as I can. Is there another one on this one? Nope, next. Next. An 8-foot ladder is placed so that it makes a 60-degree angle with the ground. 60-degree angle, that's one of our special angles, so we'll have to worry about that maybe. How far up the wall does it reach? So again, a diagram. We've got, there's the ground, there's the building. There's a ladder sitting here against the, and this is the building. There, some bricks maybe. Nice, and that's hopefully the building square, so we know that it's a 90-degree angle. And it's an 8-foot ladder, so that is 8 feet. Makes a 60-degree angle with the ground. That's 60 degrees, right? 60-degree angle with the ground. How far up the wall does it reach? So this is our unknown here, right? And now we just solve. not much harder than the last one. Opposite to the 60 and hypotenuse, opposite and hypotenuse is the sine. Opposite over hypotenuse. That's a value that we know, either from the chart or from the triangles. Remember our chart, this one. Should I do it again? Yeah, sure, what the heck. Haven't done it for a little while. And maybe you just remember these now, I don't know. I have to do the chart myself, but it's not too much work, right? And instead of doing the square, I know this one's the 1 over the square root of 2. Halfway between this would be 1/4, but then I take the square roots 1 over 2, and this is the other one. And then I can just fill in the rest. Remember, how we get the tangent one is by dividing. 0 divided by 1 is 0. This divided by this, the 2's cancel out. 1 over the square root of 3, that's 1. Square root of 3 over 1, or just square root of 3. 1 divided by 0 is undefined, and there's our chart. Maybe you've got it written somewhere handy that you can just look this up. You'll have to be able to reproduce this for the test. But now, look, it was sine of 60. I can do this exactly right there. Sine of 60 is the square root of 3 over 2. Square root of 3 over 2, x over 8, and solve for x, multiply by 8. Now, 8 divided by 4 is, or 8 divided by 2 rather, is 4 root 3. And that's an exact number. I don't have to say that's approximate. It's exact. This is an exact number. So the ladder is 4 root 3 feet up the wall. And again, if you say that to Mr. Faber, you're going to get your head glued to a table again. So we'd probably jam that into a calculator before we talk to Mr. Faber. That's about 6.9 feet. And again, 0.9, that's a bit weird. You might say 7 feet. Okay, I'm going to stop there and go on with the part 2 of this lesson in just a second.